In this talk, I want to share with you our recent work on the Skellam Mechanism for differentially private federated learning. This is joint work with my wonderful colleagues Naman and Peter at Google. So let me start off by providing some background. So as we all know, federated learning is a machine learning paradigm that aims to learn from decentralized data. In the baseline algorithm called federated averaging, the server starts off with some initial model, and then it sends that model to all the clients. And then the clients take the model, train on their local data, and then send back the changes to the model to the server. And the server takes the average of these changes and apply it to the model. And we continue doing this for many rounds. There are lots of good things about federated learning that comes from its data minimization principles, such as minimized data exposure, ephemeral collection, and only in aggregate release. So these techniques already provide good privacy for users' data. But what if we want quantifiable privacy? So we can apply this technique called differential privacy for this purpose. Applying DP to federated learning involves two steps in practice. First, we bound the user contributions. And second, we add some noise on top of the user contributions. In this case, the differential privacy is with respect to the users. That is, all the data points are associated with a particular user, rather than any individual data points on a single user. Specifically in what we call as the central DP model, you would have each client clip their updates to some vector norm before sending the server to bound their contributions. And then you would add privacy preserving noise on the server to prevent the model from overfeeding to any particular user's contributions. So this ensures that the trained model at the end and the model iterates do not contain too much information about any particular client. However, central DP requires that clients trust the server in adding a noise, which may not always be desirable. So instead, we can use this model called local DP, where we apply both clipping and noising locally. But unfortunately, as shown in the DP literature, this generally leads to poor performance. A natural question to ask then is, can we somehow combine the best of both worlds? And the answer is yes. We can use a version of differential privacy called distributed differential privacy, which offers privacy guarantees and trust models similar to local DP, while retaining the high quality model performance of central DP. The word distributed here can be interpreted as somehow distributing the trust away from the central server. For our distributed DP model, we rely on secure aggregation, which, as Ilya touched on today, is a class of cryptographic protocols to sum high-dimensional vectors in a way that ensures the server learns just the sum and no individual whatsoever. Secure aggregation is a mature technology that is currently running in production at scale. And for the purpose of this video, we'll just treat it as a black box that securely computes integer modulo sum for us. Details of SACAC can be found at the references below. So under SACAC, we can now develop a distributed DP model as follows. Each client continues to clip norm and add noise locally, as in the local DP model. And with secure aggregation, each client now only adds a very small amount of noise, specifically 1/10 of the intended central noise variance. And the server would only see the sum of all the noisy updates, which gives comparable privacy epsilon as if we were running a central DP model. This works intuitively because the variance of the sum is the sum of the variances for the individual ID noise shares. So now that we have talked about the DP model that we're aiming for, let's take a look at some existing DP mechanisms. The Gaussian mechanism is like the default mechanism that is widely used with extensive existing results. However, the problem is that digital computers can't store exact Gaussian samples, and this could potentially lead to privacy failures if we just try to use them or try to round them to integers. Moreover, it does not go well with secure aggregation because secure aggregation only takes integers or discrete values. Another existing mechanism is the binomial mechanism, which is discrete and works with SACAC. However, it has finite support, which means that it won't satisfy Rényi or zero concentrated DP, which means we can't get tight compositions when we repeat the mechanism for many times, as is the case with federated learning. Recent work also introduces the discrete Gaussian mechanism, which in the central case provide basically the same privacy as the continuous Gaussian. While this is really, really good, sampling from a discrete Gaussian at this stage is not very easy for machine learning practitioners because efficient sampling implementations are not yet widely available in packages such as NumPy and TensorFlow. Moreover, discrete Gaussians are not closed under summation, and the divergence term, the divergence of the sum depends on the number of samples that we're adding together, as well as the variance of each sample. So this means that in highly distributed settings, such as federated analytics, where we have a huge number of clients, to split the central noise, the distributed version of discrete Gaussian could underperform due to small local noise variances. So in this work, we introduced the multidimensional Skellam mechanism, which involves adding noise from the Skellam distribution. The Skellam distribution is the distribution for difference of two independent Poisson random variables, and it is symmetric when the Poisson random variables have the same variance. Skellam distribution has several nice properties. So first, it is closed under summation because Poisson random variables are closed under summation. This means that we can easily switch between central and distributed DP applications very easily. Second, it is easy to sample because you can just draw Poisson samples, and implementations for that are already widely available. Also, the Skellam distribution gets closer to the Gaussian distribution with larger variance, which is illustrated below. And this hints at the fact that for privacy applications, the Skellam mechanism could perform as good as the Gaussian mechanism as long as we have high enough variance. The Skellam mechanism was previously introduced for the scalar case, but unfortunately, RDP and zero CDP analysis were not available. So it would get poor performance if we just try to directly generalize the scalar analysis to the vector case along with compositions. In this work, we provide a tight RDP analysis that performs as good as the continuous Gaussian under practical conditions. Our analysis really allows the Skellam mechanism to be used for complex problems such as federated learning for the first time, which we'll show without empirical analysis. So just for completeness, I want to share this slide with you, which summarizes the high-level preliminaries for our results. With the mechanism M, we say it's epsilon delta differentially private when the probability of getting an outcome does not change by much, and up to this e to the epsilon multiplicative factor and the delta additive factor, if we change the data set by adding or removing an element. And this applies to all possible outcomes, so it's a pretty restrictive definition. We also consider a notion of DP called Renyi DP, which concerns about the Renyi divergence, as shown here, between the output distributions of the mechanism when the data set is again changed by only one element. Renyi DP is nice because it allows us to do tight compositions, which means when we run the mechanism repeatedly, such as federated learning, where we train for many rounds, we can get a smaller cumulative epsilon value at the end. And once we're finished, we can convert back to the standard epsilon delta DP from RDP using a conversion formula. And so on the top right, we have the RDP guarantees for the Gaussian mechanism, which is the baseline that we care about. Okay, now let's briefly go over our main results. This is the main RDP guarantee for the Skellam mechanism, and let's break it down a little bit. In particular, the first term is exactly the RDP term for the continuous and the discrete Gaussian mechanisms. Skellam would have an additional term, so we'll have slightly worse privacy, but notice that this term quickly goes to zero if the noise have a high variance. Now, a high variance can either come from a strong privacy requirement, or we could simply scale both the input and the noise variance to directly dampen the second term. If we look at the effect of scaling directly, we can see that the scaling factor has a pretty strong effect on making the second term zero. This is nice because in practice, when we combine Skellam mechanism with quantization techniques, for continuous input values, using techniques such as uniform quantization, you would already have a reasonable scaling factor during the quantization, and that would make the second term practically zero. Okay, so let me briefly highlight the RDP analysis, and please check out our full paper for more details. So when we perform an RDP analysis, we will look at two shifted Skellam PMFs and try to bound their ratio. For Gaussian, this analogous quantity has a closed form expression, but unfortunately, we don't quite have that for Skellam because we're dealing with Bessel functions. So we need to look at existing bounds on the ratios of Bessel functions. And the previous analysis of Skellam mechanism uses an older bound that leads to a bad dependency on Ln sensitivity. In our work, we essentially leverage a tighter bound from 2016 that allows us to shave off that dependency and hence leading to a rapid decay of the second term of our RDP guarantees. So depending on the value of X in relation to delta, which is the sensitivity of the DP query, and alpha, which is the Renyi divergence order, we need to do the analysis in 6 different cases and analyze each of them to arrive at the final RDP bound. Okay. So to see this in action, let's compare the Skellam mechanism against several mechanisms in the distributed scalar case. So here we plot the privacy epsilon against the central noise multiplier. On the left, we have a relatively small noise. X-axis is the central noise multiplier, which is the ratio between the standard deviation, noise standard deviation, and the sensitivity. And we can see that Skellam approaches the Gaussians under the effect of scaling and degrades more gracefully than the distributed discrete Gaussian when the local noise is small. Notice here that when we notice here that we have a target central noise standard deviation, but we are kind of adding a noise locally, so we have to split the noise into n equals 100 clients. And this is what is really contributing to the divergence terms of the distributed discrete Gaussian. On the right, when we have very high privacy, then we can see that Skellam performs as good as the Gaussians and also outperforms the existing analysis for scalar case for the Skellam mechanism, which is the green line. When we consider the distributed vector case, along with compositions, we also see similar results. On the left, we have clients starting with the real vectors, and then the entries are rounded to integers before adding noise. So similarly, Skellam matches the Gaussians under the effect of scaling, and when scaling is insufficient, it behaves slightly better than the distributed discrete Gaussian. On the right, we have a practical FL setting where we have a model of million parameters and t equals 1500 rounds. And we see that even though DDG is asymptotically closer to Gaussian, Skellam practically gives the same performance. We first empirically validated the Skellam mechanism on distributed mean estimation, which is one of the core tasks of distributed optimization and federated learning. The setting is that we have n clients, each holding a d-dimensional vector that is uniformly randomly sampled from a sphere. Our goal is to estimate the mean privately by the distributed Skellam mechanism, so we quantize and add noise locally. The results shows that as long as the bit width is sufficient, which measures the field size of secure aggregation, then Skellam can indeed match the analytic Gaussian mechanism even at 10,000 clients per round in terms of the mean square error from the true vector mean. We then empirically validated the Skellam mechanism under the distributed DB model on federated learning by training a language model on the Stack Overflow dataset. On the left, we have we show the test accuracy across different levels of privacy and communication budgets. And on the right, we show the validation accuracy over training a particular setting. The main result is that Skellam can indeed match central Gaussian and the distributed discrete Gaussian across different settings. But however, due to time limit, please check out our full version of the paper for more results on federated learning. So to summarize, the Skellam mechanism involves adding noise sample from the Skellam distribution for privacy, and the Skellam mechanism can perform as good as the continuous and the discrete Gaussian based on our tight RDP bound. Overall, Skellam is a very practical alternative to the distributed discrete Gaussian mechanism because it is close on estimation, so we can easily switch between central and distributed DP applications. And unlike discrete Gaussians, we can worry less about any divergence terms in massively parallel settings with small local noises. Skellam is also very friendly to privacy and machine learning developers because efficient samplers are already widely available in many software packages. Okay, finally, please also check out the code and the full version of this paper. Thank you.
Great, thanks for the talk, Ken. And we already have a question by Adria, so please go ahead.
Let's see.
Yeah, I was wondering about how hard it is to find the right scale in practice. How did you find that hyperparameter in the experiments?
Yeah. So right now we start off with with a certain bit width, say 16 bits, and that 16 bits is the per coordinate bit width for summing all the values from the clients. And so that essentially gives us, some field size of 0 to, for example, 65K or something. And then with that field size, we can sort of then estimate the variance of the total aggregate. So total aggregate would have a variance that is dependent on the L2 norm of the original inputs. When the clients keep the inputs, we have norm, and that norm would give us some can be used to derive an estimate of the variance. And then we also add a noise on top of it, which is the Skellam noise, and that thing also has a variance. So with the total variance, we can assume, for example, the aggregate has like a sub-Gaussian, like a Gaussian-like distribution, and then we can say, using just a heuristic, say, I want to bound 4 standard deviations of that distribution, of the sum that distribution, because we know the variance, right? So using that, we can essentially take 2 to the 16 divided by 4 to that variance, and then we get like a scaling factor. In practice, it doesn't matter if the scaling factor is off by a little bit, because as long as we have enough scaling factor to not get hurt from quantization errors, then larger scaling factors and slightly larger, slightly smaller scaling factors won't change the results by too much.
Thanks so much.
Thank you.
Oh. We have another question by Aurélien.
Hi, thanks a lot for the talk. So my question is a bit on whether there is some kind of optimality to this distribution, or I'm not even sure exactly how this should be defined, but I guess what I mean here is whether the proposed distribution is in a way optimal, like given the desired property that you want, like discrete closed under summation, and now you have this additional kind of additive term, right, that you get compared to a continuous Gaussian, for instance. So is it in a way optimal, or can we do better? Do we expect to see maybe new discrete distributions in the future that can improve on that, or not?
Yeah, so I can give like some kind of high level thoughts here. So just in terms of the RDP guarantees, we don't expect to do much better under this particular framework, right? Because we analyze under RDP, and then let me bring up my slides. Just 1 second, I think I lost it there. Okay, so under the RDP framework, we don't expect to do much better. And there's lots of assumptions to this, right? Like, for example, we assume that we compress on a per coordinate basis, we add noise to a per coordinate basis, and then these RDP guarantees are already pretty close. So on that front, we don't expect to do much better. But in terms of whether can we do distributed DP in general with other approaches, not just uniform quantization, not just rounding individual values and add individual noise to it, can we compress things in a different way? That's something we are not too sure about. And then the other aspect is, can we not use RDP or zero concentrated DP, right? I think Jordan was talking about FDP. Maybe that could be something else that we could look into. But under this particular setting, using RDP for per coordinate compression, I think that's yeah.
All right, thanks.
I wanted to add something very quick, if I may, to Aurélien's question. So when the bit width is high enough, say 16 bits or more, we're matching the continuous Gaussian mechanism. We match it exactly. So if your goal is to try to improve on the central continuous Gaussian mechanism, you cannot. That's it. When you're above 16 bits, this is optimal in that sense. However, as Ken showed on one of the slides, when the bit width is low, say 12 bits or less, we are not close to the continuous Gaussian mechanism. This approach does very poorly. As you can see on the slide on the left figure, for 12 bits, the orange and the light green curve indicates that neither the discrete Gaussian nor the Skellam are actually coming close to the continuous Gaussian. So there's an open question of what if we want to use less than 16 bits? how close can we get? Because this seems to be way too far off from the continuous Gaussian, especially at small epsilons. You would expect to be able to use very few bits at small epsilons. So there is a fundamentally different mechanism for very small epsilons that's going to match, in my opinion, the performance of continuous Gaussian with less bits. And that's where there is this open question. But if you have 16 bits or more, then we're doing great.
I see. Very very interesting. Nice. So this is even despite the I mean, okay, some of this loss is also due to the compression, arguably, right? But you think there is still
there's the quantization errors, and there's the modulo wraparounds from secure aggregation as well. Yeah.
Right. Thanks.
There's another question.
Okay, thanks everyone.
There's another question.
There's one more question by Hui. So I guess since we have a break now, we can go a bit over time. So please go.
Yeah. So sorry.
Thank you.
Please.
I just wondering, is this mechanism only works for federated framework, or can we can we use it for other frameworks, not distributed?
I think just the way that we're adding noise and the privacy analysis of it, it's like it applies to it anywhere, right? If you just add noise in a distributed fashion, as long as you specify the right sensitivity and the noise, the RDP formula still kind of applies, right? So in this case, we apply it to federated learning because RDP allows us to do very high dimensional queries, which which we can't before. So this is a good application, but there isn't an inherent limitation to our analysis to federated learning.
Okay, thanks.